Hello, my name is Mohammed Ombadi. I'm a PhD student at University of California, Irvine, and today I'm going to speak to you about hydrologic complexity. So let me start first by posing a few motivating questions. Are wet hydrologic basins easier to model than semi-arid ones? How does the basin size impact the number of parameters needed to represent the hydrologic response of a basin? And what are the variables that exert the first order control on basin behavior? These questions pertain to the notion of hydrologic complexity, and no doubt they have occurred to many hydrologists since we frequently encounter them whenever we are interested to extrapolate empirical knowledge from gauged to ungauged basins. So how do we go about answering these questions? Well, in literature, there have been two main approaches to acquire testable hypotheses on hydrologic complexity. The first of which is what we call comparative assessment. And in this approach, we utilize meteorological variables, we feed them to a rainfall runoff model, and we obtain streamflow simulations. We then bring in observations and assess the accuracy of simulation. These steps are carried out for a very large number of basins. And then we try to infer the relationship between the properties of the basins and the accuracy of simulations. And in the recent 2 decades, there has been a great deal of research in this direction. The second approach is data-driven exploration, and what I'm going to talk to you about today falls within this category. This is particularly advantageous because it is a model-free approach. It is not impacted by assumptions encoded in models. However, one issue that we have to deal with is the lack of observations regarding key variables, such as evaporation, infiltration, and subsurface flow. And the question is, how do we deal with this? So I argue that most of the information we are looking for is encoded in a streamflow. And first of all, it is desirable to work with streamflow observations because it is one of the most routinely measured hydrologic variables in basins around the world. And for some basins, we know that this dates back to a very long time. For instance, we know that ancient civilizations at the banks of the Nile River used the Nilometer almost 3,000 years ago to measure the Nile flow. But the main argument here is that streamflow is an integrated measure that encapsulates the contribution of climatic variables such as precipitation, the vegetation component, as well as the topography and soil characteristics of a basin. So in a way, streamflow encodes all the complex interactions that conspicuously distinguish a hydrologic basin. And if we were to use streamflow observations to characterize hydrologic complexity, then we need methods that are able to exploit the information content of the data. I hope to convince you today that the answer lies in chaos theory. And in chaos theory, which much of its early development is attributed to the famous meteorologist Ed Lorenz, there is a particularly powerful theorem named phase space reconstruction. And I'm going to explain this here using the Lorenz system. The Lorenz system consists of three first-order differential equations. And by solving these equations for some values of initial conditions, we obtain time series of x, y, and z. And by using these time series as coordinates, we can construct the attractor of the system in 3 dimensions. Now, the theory of phase space reconstruction tells us that under very weak assumptions, we can utilize the time series of variable x as well as its lagged values to reconstruct the attractor, and that this reconstructed attractor preserves a lot of the properties of the original attractor. Now, In our context, this means that we can use the phase space reconstruction theorem with the streamflow observations to reconstruct the attractor of the hydrologic basin. This figure here shows an attractor constructed from streamflow observations for a hydrologic basin in Pennsylvania. And the coordinates of this attractor consist of streamflow observations lagged by 0, 1, and 2 time steps. So before I tell you what kind of properties we can estimate from this attractor, it is quite important to note that every attractor can be used to make forecasts by learning from the historical trajectory of system states. Now, one of the things that we can do is, instead of constructing the attractor in 3 dimensions, as shown in the figure in the left, we can do this for multiple dimensions, 1, 3, 5, 10, up to a certain limit, which is taken to be 20 here. And this is what is denoted by E in the horizontal axis here. And then for each dimension, we look at the value of forecasts, and we try to identify the value of E that maximizes the forecast. And in the theory of dynamical systems, it is very well established that this value represents the number of active degrees of freedom. In other words, this value tells us how many variables are controlling the dynamics of the system. Similarly, there is another parameter denoted as theta, and the value of theta, a value of 0, indicates that the system is linear. As theta takes larger values, the system is more and more nonlinear. In this particular basin, both values of E and theta are equal to 3. Now we can construct a 2-dimensional plane where the horizontal axis represent E, the number of active degrees of freedom, and the vertical axis represent theta, the nonlinearity index. And we can take the 2 values we estimated in the previous slide and map them into this 2-dimensional plane. What we can also do is look at other hydrologic basins. So here we have 400 hydrologic basins in the contiguous United States from MOPIC's dataset. And by carrying out the same analysis, we can map the values of complexity indices for those 400 hydrologic basins in this 2-dimensional plane. And here are the marginal distributions of the 2 complexity indices of E and theta. And we see that both distributions are positively skewed with a very long right tail. But the main result that I want to emphasize here is that this represents a framework, a yardstick, to measure the complexity of any given hydrologic basin relative to this large cluster of hydrologic basins. But what is more interesting is to examine whether there are any coherent patterns between the 2 complexity indices of theta and E and the properties of hydrologic basin, like the elevation and the slope and the basin size and so forth. So here we have 14 basin properties, either topographic, climatic, or pertaining to the land surface. And this table shows the value of a Spearman correlation coefficient between the basin properties and the 2 complexity indices of E and theta. And the values shown in red boxes are statistically significant at a significance level of 0.05. So now let's look at some of these relationships in more detail. Here, this figure shows a strong inverse relationship between the number of active degrees of freedom, which is denoted by E in the horizontal axis, and the basin size in the vertical axis. And specifically, larger basins tend to have lower number of active degrees of freedom. And our interpretation of this relationship is that larger basins are more effective in filtering and smoothing the heterogeneities within the basin. And as a result, a number of active degrees of freedom are subdued, and we are left with only a very low number of active degrees of freedom. And this observation corroborates qualitative statements that was previously made, indicating the simplicity of rainfall runoff modeling in large basins compared to small ones. Here we have the number of active degrees of freedom in the horizontal axis and the slope of the main channel in the vertical axis. And we see that there is a positive Spearman correlation coefficient of 0.32. What does this mean is that by holding all other variables constant, an increase in the slope of the main channel leads to a flashier response of the basin, and as a result, higher number of active degrees of freedom. And this observation is partially in line with previous studies that highlighted the difficult nature of rainfall runoff modeling in flashier basins. However, contrary to previous studies that attributed the flashier response to climatic variables, our results here demonstrate that it is the slope of the channel that causes the higher number of active degrees of freedom. Here in the horizontal axis, we have the nonlinearity index, theta, and the vertical axis shows the IGBP land cover classes from 1 to 14. And the IGBP classes, the gradient of the classes from 1 to 14 represent the spatial and temporal extent of vegetation, specifically from evergreen forests to deciduous forests, to shrublands, to wetlands, and bare soil. And what does this mean here is that basins with more vegetation tend to have nonlinear dynamics. And this is perhaps related to the so-called sponge effect hypothesis, which refers to a broad suite of beneficial characteristics attributed to the presence of forests. And specifically, this hypothesis postulates that the presence of forests reduces the annual runoff. However, at the same time, it promotes infiltration and groundwater recharge, leading to higher runoff during the dry season. In other words, the presence of vegetation leads to complex state-dependent nonlinear behavior. And this hypothesis has been examined in a number of previous studies. So to summarize, in this study, we have used methods rooted in the theory of chaotic dynamical systems to investigate the complexity of hydrologic basins in terms of two indices, the number of active degrees of freedom and the nonlinearity. And we found that the number of active degrees of freedom is related to the basin size and the slope, whereas the nonlinearity is modulated by the presence of vegetation. The implications of the results presented here is that they provide a quantitative framework for catchment classification based on dynamic similarity. And there is a potential to exploit this concept of dynamic similarity to extrapolate empirical knowledge from gauged to ungauged basins, which is a central task in predictions in the broader issue of predictions in ungauged basins, an issue that is deemed to be one of the grand challenges facing contemporary hydrology. These are some of the references that are used in this talk, and this research was partially supported by the Department of Energy and California Energy Commission. Thank you for your interest in this talk.